This program is brought to you by Stanford University. Please visit us at stanford.edu.
I almost always begin with the same sermon about, especially when teaching about quantum mechanics or relativity. And the sermon is always the same. It's the fact that we as animals have inherited through the process of evolution certain intuitive ways of thinking about the physical world. And if you don't believe it, you think that maybe ordinary animals are not physicists, you watch a lion chasing an antelope, and you notice that that lion, the minute that the relative velocity between the antelope and the lion changes sign, the lion just stops dead. Somehow he did some calculation, or she, it's usually a she, the lion, did some calculation, some physics calculation involving some very complicated concepts of velocity, direction, all kinds of complicated computations like that. A primitive Cro-Magnon man, or not a Cro-Magnon man, a Neanderthal, who comes to a cave and sees that the cave is blocked by a boulder and tries to push the boulder and can't push the boulder, decides to aim his body that way. Why? So that he gets a bigger component of force in that direction. Has he ever heard of force? Has he ever heard of components? Where did he get this idea of components? Did he know about sines and cosines? Yes, somehow he did know about sines and cosines. These are things which were inherited, biological in origin, and they are the basis of our intuitions about physics, our intuitive picture of the world. Much of physics has to do with those things. In fact, all of modern physics, everything in modern physics, has to do with those things which are beyond the intuitions that we were able to get from the ordinary world. Has to do with ranges of parameters which are way outside the range of parameters that humans or animals ever experienced. For example, it's not too surprising that human beings didn't know how to deal with velocities approaching the speed of light, that they got the wrong ideas about how to add velocities when nobody in 1900 had never moved faster than 50 or 60 or 100 miles an hour. Well, they probably did when they were falling off cliffs, but they didn't live to talk about it. Maybe they got up to 200 miles an hour, maybe. But nobody ever had experienced anything like the velocities approaching the speed of light. And so it was not surprising that their intuitions, that their way of thinking about adding velocities and so forth, the theory of relativity was, and how you synchronize clocks, all that stuff, all that good stuff that Einstein did, that it was outside the framework of their ability to think about through intuitive pictures, through intuitive mathematics. They had to invent new mathematics. The new mathematics was abstract, meaning to say you couldn't visualize it. Four-dimensional space-time. I can't visualize 4 dimensions. I've learned tricks to visualize it. So physicists, to some extent, rewire themselves, or people who learn physics, through a process of rewiring themselves to some extent to develop intuitions to be able to deal with these new ranges of parameters. But still, they're foreign, they're alien, they're peculiar, even to me. Quantum mechanics deals with a range of phenomena which is also outside the experience of ordinary humans, for which evolution simply didn't provide you the means to visualize. Evolution did not provide you the means to visualize an electron, to visualize the motion of an electron, to visualize the uncertainty principle. When you think of a particle moving, what is a particle? A particle is a thing with a position. At every instant of time it has a position. If at every instant of time it has a position, it has a trajectory. If it has a trajectory, you can calculate the velocity along that trajectory. Just by knowing the separation between points and what the time interval is, you can calculate the velocity. And that's the intuitive picture of a particle. And where does it come from? It comes from thinking about rocks, throwing rocks, shooting arrows, all kinds of things that human beings normally do. So we never developed the need. It would have been very bizarre if our brains had been wired to understand the uncertainty principle. Why would Darwin have given us incidentally, if you prefer to think of the intelligent designer, go right ahead. I prefer to think about Darwin. But why would either of Darwin's ideas or the intelligent designer have provided us with the ability to understand the uncertainty principle when it's never anything that's part of our ordinary experience? The answer is it didn't. And so quantum mechanics, for that reason, appears extremely weird to us. Physicists, as I said, rewired themselves and developed ways of thinking about it which are intuitive, but still, quantum mechanics is much, much more unintuitive, incidentally, than the special theory of relativity. And what we're going to try to do here is expose some of the weirdness of quantum mechanics, the weirdness of the logic of quantum mechanics, the weirdness of how quantum information works. This is not a class, a conventional class in quantum mechanics. A conventional class in quantum mechanics would stress such things as the Schrödinger equation and waves, and how particles sometimes behave like waves and so forth. We may or may not get to a bit of that, but that's not the important subject that we're going to concentrate on. What we're going to concentrate on is the basic logic of quantum mechanics, the basic logic of quantum information theory. Physics is information. When you say something about a physical system, you're saying you're giving some information about it. You give the information in various forms, usually in the form of numbers. In classical physics, you often give, I will give you some examples, but you usually give it in the form of real numbers, the position, the velocity, a set of real numbers. In quantum mechanics, sometimes you use real numbers, but very, very often you give discrete information. Discrete information such as yes or no, or up or down, or male or female. Well, that's probably not such a good example. The differences between, that's probably up. I think I'll withdraw that. Heads or tails? Heads or tails? Do I have a coin? No. Gedanken coin, thought coin. Head, tail, right? When I flip the coin, head, that's a piece of information. It could be tail. It's a two-valued system, either yes or no, up or down, heads or tails, or sometimes, they're logically all the same, of course. They're logically all the same, whether we're talking about heads or tails, up or down, or whatever it is, they're logically the same. And they're simply decisions which have two possible, or questions which have two possible answers, and a bit of information which has two possible answers is called a bit. It's called a bit, and it can either be a classical bit or a quantum bit. All real bits in nature are quantum bits, obviously, since nature is made out of quantum mechanics. But sometimes the quantum aspects of it don't manifest themselves. In an ordinary computer, the quantum aspects of the bit don't really manifest themselves for reasons that we'll come to. And it's just called a classical bit of information. This the coin flip, yes or no. The quantum bit is the quantum analog of the flipped coin, the yes or no type question, but it is much, much more subtle. And the first thing we're going to want to explore is what is a quantum bit. Now, but before we do that, let's talk about classical bits. Classical bits can be described either by writing down a 0 or a 1. We could also use 1 and -1, or we could use 5 and 15, doesn't matter, but 0 and 1 is a convenient notation for the two possible values. 0 could stand for heads, 1 could stand for tails, and so forth. So when we're thinking about this, we're thinking about some physical system. When we're thinking about information, we're thinking about a physical system such as a coin, and this is the information contained in that coin, either a 0 or a 1. There's a notation. This seems like a ridiculous and redundant notation. Its importance will only become clear when we start to think about quantum bits, but we're going to use the Dirac notation. The Dirac notation describes the state of a bit, not whether it's California or Oregon, but the configuration of the bit, and it's usually labeled with the notation 0 or 1, or whatever other information, whatever other way you decide to think about the bit. These are the two states that a bit can have, either a 0 or 1, and it's represented, I don't know if I drew that well. Let's draw it again. 0 or 1. These are the two states of a bit. All of this extra junk here is excess. You don't need it. It doesn't tell you anything. It just says that you're putting it inside a bracket. Incidentally, this pointy bracketed object over here, the thing that contains the information on the inside, is called a ket. It's called a ket because it's the second half of something which we will later learn is a bracket, or a bracket. There's another half that we haven't exposed yet. Now, what about multi-bits? Supposing you have more than one bit, and we're talking now classical physics. So far, we're not talking about anything quantum mechanical. Supposing we have several coins, and I line them up. I label them so we know which one is which. In fact, just in order to not confuse coins, let's make sure they're different coins. Penny, nickel, dime, quarter, half dollar, silver dollar. Okay, so we have a bunch of coins. We can't confuse them. And we can lay out some information by saying head, tail, tail, head, head, tail. That would be some information about a collection of bits. All right, how would you label that? Well, you would label it with a string of zeros and ones. So, for example, if we, let's take 0 always to stand for head. It's easy to remember. 0 stands for head, and 1 stands for tail for obvious reasons. Right, so my string of coins, heads, head, 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 tail, head, I would label 0 for head, 0 for another head, 1, 0, 1, 1, for example. That's a configuration of 1, 2, 3, 4, 5, 6 coins. All right? Let's say it was 6 coins. All right? That's a configuration of a multi-bit system, in this case 6 bits. Again, for reasons that add absolutely nothing to this description, we're going to stick it inside a ket. We're going to stick it inside a ket, which is just a kind of notation. It might be a good idea to put some commas between these, but maybe not. Maybe it's just best to leave it that way. That's a specification. It could be the specification of the bits of information inside a computer. It could be just a series of heads or tails or so forth. But before we do anything else with this, let's ask a very simple question. How many possible configurations, how many possible states are there of, well, let's start with 1 bit. If there's only 1 bit, then there are only 2 states. What if there are 2 bits? Well, then you can have up, 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 down, down, up, down, down. 4. 2 times 2. So for 2 bits, we have 2 squared. What if we have 100 bits? The answer is 2 to the 100th power. 2 times 2 times 2 times 2, 100 times. So if you have an n-bit system, the number of possible classical configurations is just 2 to the n. Let's write that down. Let's put a notation in. Let's write the number of states, n sub s, the number of states of a system of little n bits is 2 to the n. Let's suppose let's invert that first of all. Let's invert, little n is what? Little n is the number of bits. Big N is the number of states. Little n is the number of bits. Okay? So if the number of bits is 4, then the number of states is 2 to the 4, which is 16, and so forth. We can invert this, and we can write, if we knew the number of states of a system, then we can take the logarithm of this equation. Log to the base 2 is particularly convenient. If we take the log to the base 2 of the number of states, that's equal to the number of bits. You can generalize this. Not every system has as its number of states 2 to a power. Supposing I have a system, a die, the things you use in Las Vegas to throw away your money with. It's got 6 possibilities, 1 through 6. That is not 2 to any particular power. It's just 6. Okay? But we can still generalize this definition of the number of bits of information. In fact, the number of bits of information that a system can contain is, by definition, the logarithm to the base 2 of the number of states, which for the die would be log to the base 2 of 6. What is log to the base 2 of 6? Is it an integer? No, it's some stupid irrational number. I don't even, what is it? How big is it about? 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 2.5, 3, 7, 9, 8, 6, 14, whatever. So the amount of information, which is always the logarithm of the number of states, does not have to be an integer. But we're going to be considering systems which are made up out of some number of bits, each of which has 2 states. So for the simplicity, we're going to be talking about systems. The number of states is always 2 to a power. That's just for simplicity. There's nothing special about it. But almost every system can be represented that way or approximately represented that way. Let me give you an example. Supposing we have some question of physics which has as its answer a real number. But we're only interested in that real number to a certain approximation. The temperature in the room. I'm interested in the temperature in the room to a certain number of significant figures. I can represent the temperature, or any other number for that matter, by writing it as a number in base 2. Right? What's the temperature in this room, incidentally? It's about 300 degrees from absolute 0, so it's 300. I can write 300 not as 300, which is, what does 300 mean? 300, you know what it means. It means 3 times 10 to the 2, plus nothing times 10 to the 1, plus 0 times 10 to the 0. But we write it to things in base 2. All right? I don't know what 300 looks like in base 2. Somebody can figure it out. Base 2, everybody know how arithmetic in base 2? Anybody not know arithmetic in base 2? Okay, so everybody knows arithmetic in base 2. We write out any number that we like as a series of zeros and ones. 1, 0, 0, 1, 0, 1, 0, 0, 1. That's some number to the some particular integer. It's an integer. So if I'm interested in the temperature, and I'm not interested in being too careful to define fractions, I want to know whether it's 72 degrees or 73 degrees. I don't care about 72.4069. I can write it as an integer, and that integer can be represented as a sum of bits. Not a sum of bits, but as a collection of bits. Every number, every single number, if you're willing to truncate the number of decimal places, approximate that number, and say I'm interested in that number only to 35 decimal places or whatever, or to 35 places to base 2, that number simply is represented by and represents a collection of bits. So and incidentally, if you want to have a finer grained description of the temperature than integers in centigrade, you just use a more refined notion of degree. You go down to ask how many degrees is it, but not in centigrade units, but in units of 10 to the minus 100 in centigrade. Again, you can give it as an integer, and integers can always be represented as sequences of zeros and ones. So almost any information in physics can be represented in terms of bits. In particular, the measurement of quantities such as temperature, for example. Let me give you another example. This is a more complicated example of the same thing. Supposing I'm interested in a field. A field means a thing which can vary throughout space. All right? A thing which can, well, the temperature can vary throughout space. The temperature is a field. It varies throughout space. It's not one of the more interesting fields from the point of view of fundamental particle physics or anything, but that certainly is a field. It varies from place to place. And how can we represent that? Can we represent that in terms of bits? Yes, if we're willing to tolerate certain approximations, and we're always willing to tolerate some degree of approximation. What we do is we break up the room into a lot of little tiny cells. I won't try to draw a three-dimensional room. In my notes, I drew a three-dimensional room. It took me about a half an hour to put in all the lines. Just a two-dimensional room. And here's what we do. We first of all order the cells. We make the cells small enough so that the temperature doesn't vary very much from cell to cell. So we might fill this room with several billion cells. Label the cells. This is the first cell, 1, 2, 3, 4, 5, 6, I don't know, up to 1,000. 1,001, 1,002, 1,003, 1,004. And we can label all of the cells and list them. Once we've listed them, we can write the temperature of the first cell. There's the temperature of the first. I'm putting a little comma in just to distinguish between cells. Then we can write the temperature in the next cell, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. I've kept 9 decimal places in the basis in arithmetic in base 2. 1, 1, 0, 1, however, till I'm finished. Then I go to the next cell. Do the same thing. Temperature there is 1, 1, 0, 1, 0, 0, and so forth. Eventually, all I have is a list of zeros and ones. This long list of zeros and ones, if somebody knows how to use it, is equivalent to knowing the temperature at every point in the room. Okay? The same is true of the electric field, the magnetic field, anything which varies from place to place. So almost everything that I can think of in physics can be represented in terms of bits. So if you know everything about how bits work, you basically know everything about how physics works. Of course, you may not know what the rules are for manipulating these things, but this is the basic setup of physics: information in the form of a series of questions, each of which can be answered yes or no. Now, of course, you may want to refine your description. To refine your description, you may want to add more decimal places to the temperature, to the specification of temperature, and you might want to make your lattice finer. That's just making a better approximation. So the right thing to say is that most physical systems that we know about, as far as I know, all physical systems, can be represented at least approximately, and perhaps to always increasing approximation, by a series of bits. That's why we get to use computers to do physics. If this weren't true, we couldn't use a computer. We couldn't use a digital computer in any case to do physics. We'd have to use analog computers or something. Okay, so that's, let me give you another example of how you might use bits to represent another. These are all so far classical systems, as I said. I don't want to redraw the lattice, but I do want to get rid of this top row here since I've already mutilated it. Here's a lattice, and what I'm interested in is the motion of particles. This lattice is just an artificial imposed lattice that I've imposed on the room here, just so that I've divided the room into mathematical cells. And what I'm interested in is the motion of particles moving around in this room. At any given instant, I can ask the question. Let's take a very simple case. Let's take the case where a particle, where you can't squeeze more than one particle into one of these cells. We can imagine that. The cells are about as big as a particle, in which case you can't squeeze in more than one. Then every cell either has a particle or it doesn't have a particle. We can label the cells that have particles with an X. We can label the cells that don't have a particle with nothing. Or better yet, we can label the cells that have a particle with a 1 and the ones that have no particle with a 0. In that case, this becomes a specification of where the particles are in the lattice. It's no longer the temperature, but the same long sequence of zeros and ones. Now the number of zeros and ones would just be equal to the number of cells in the lattice. What would this number mean? It would mean that in the first cell there's a particle. In the second cell there's no particle. In the third cell there's no particle. In the fourth cell there's a particle. In the fifth cell, no particle. In the sixth cell, particle. And so forth and so on. And so given such a string of numbers, you are given a specification of where the particles are in this room. In that way, again, motion of particles, motion of fields, temperature, just about anything in physics can be represented in terms of bits. Any questions? Right. A bit is by definition a question about a system which has only two possible answers, which you can always take to be yes or no. Used to be a game, 20 questions, where somebody would think of a category, and then you would stand there and ask yes/no questions, and until you tried to figure out what the category, what the category was. So that was using the idea of bits. Yes, question. Oh, I just arbitrarily said, supposing we are interested in the temperature to a certain degree of accuracy. Right. So I'm interested in the temperature to accuracy, but now I'm not speaking about temperature. I'm just giving another example. These are just examples intended to show you something which is more or less clear. Otherwise, we could not use computers to simulate physical problems, classical physical problems. Yes, right. But you need, for the general real number, you need an infinite number of bits. Right? Any rational number can be represented by a finite number of bits, and the rule, well, that's not quite true. You have to remember to repeat them, but
if it's rational, it's going to repeat after some point.
yeah, if it's rational, it's going to repeat after some point, right? So, but if it's an irrational number, then you need an infinite string of bits. But in general, we will allow infinite strings of bits, although not in a genuine computer. Well, so far, remember, we're doing classical physics. All right, so far, no quantum mechanics. So I will come, let's see, where, yes, we were going to come to that very, very shortly. Well, let me tell you how very quickly. An electron, first of all, we're not talking about motion yet. We're talking about configuration. Configuration means the state of a system at a given instant of time. Okay? So the presence of an electron at a given instant of time, let's suppose the nucleus is known to be right over here, and we're not going to ask about the nucleus. The nucleus just sits there. It's a lump on the... All right, so we could say at instant number 1, when we begin the experiment, the electron is over here. In that case, we would write down a string of zeros with a 1 someplace. Pure zeros, 1 electron, pure zeros, except for one place in the sequence where there's a 1. Okay. Now, if we wanted to describe the motion of the electron, we would say, starting with this configuration, we move, and let's use this symbol here to indicate that at the next we've broken up space into a lot of little individual cells. We could also break up time. I thought I had my watch, but I don't. We could also break up our watch into a digital watch which digitizes time, just again as either a convenience or an approximation. And we could say if at digital time number 1 the electron was, or the system was described by 1 electron located at this location, then what happens next? Next, it moves to some new configuration. In this case, it might move over one place. 1, 2, 3, 4, 5, 6. It moves over to the 6th place. 1, 2, 3. Okay. And so forth. So the motion of a system is described by a rule of updating information, how you update it from one instant to the next. All right, so physics basically consists of a physical system consists of 2 things. It consists of a collection of possible states which can be labeled by a collection of bits, and it consists of a time evolution, which is an updating which tells you how to take one collection of bits and replace it by another collection of bits at a slightly later instant of time. I don't know if that answers to actually work out an orbital motion orbiting around here gets confusing, because when you jump from one layer to the next, if this is 1 and this is 100, then 101 is over here. So you don't jump from 100 to 101. You might jump from 100 to over here, which would be 200. So it can be complicated, the updating procedure. It can look complicated, but nevertheless, it's an updating procedure that just updates your state of knowledge at each instant of time. That's classical physics. Now, there are some rules, and we're going to come to them. But before we do, let's define the space of states. This is, and I want to emphasize, we are still doing classical physics. There is nothing quantum mechanical, even though we're talking about discretizing systems and making out of them systems of individual bits. So far, we are dealing with what should be called classical bits. C-bits, I think they're called, as opposed to qubits. Qubit is a quantum bit. These are classical bits so far. Okay, so let's take all of the configurations and just abstractly, in a purely abstract way, we take all of the configurations. Incidentally, what are they? There's about 10 by 10. This is roughly a 10 by 10 lattice. 10 by 10 lattice has 100 sites. How many states does it have? If we, I'm not talking about one particle now. I'm talking about any number of particles can be on this lattice. How many different configurations are there? 2 to the 100. A very, very, very big number. 2 to the 100th power. That's how many different ways we can arrange zeros and ones on this lattice, or specify whether there's particles in various positions. A very large number of possible states. But let's just abstractly think about all these states and just draw them as points. If there are 10 to the 100, I have to draw 10 to the 100 points, which I'm not about to do. These are the various states. These are not the lattice points. These are the various states. For example, for one bit, if I had only one bit, then the space of states would consist of only 2 points, up and down, and I would just draw 2 points. This would be the space of states of a simple 1-bit system. Now let's ask, what are the possible laws of updating? In other words, what are the laws of motion? The laws of motion are the laws for updating configurations. What are the possible laws of updating? Well, here's one possible law of updating. This could stand for heads, this could stand for tails. Let's think about it in terms of coins for the moment. This could stand for heads, this could stand for tails. All right. If we start with heads, if I had a coin, we would do it. Here's heads and tails. Heads, tails. All right. One possibility is very simple. If you start with heads, it stays heads. Nothing happens. If you start with tails, it stays tails. Nothing happens. That's a law of updating. It's not a very interesting law of updating. How would you draw that? Well, here's how we'll draw it. Heads goes to heads. We'll make an arrow. If we start with heads, it stays heads. If we start with tails, it stays tails. So we draw an arrow from what you start with to what you end with. What's another possible law of updating? Here's the law of updating. If it's tails, it becomes heads. Then it becomes tails. Then it becomes heads. Then it becomes tails. That's a little more, not very much, but a little more interesting. A slightly more interesting system. It just flip-flops back and forth. How would we draw that? We would draw that again. Heads, tails, heads, tails. If you start with heads, you go to tails. If you start with tails, you go to heads. So the law of updating in this case is just described by such a diagram, basically. A diagram which tells you, if you start at a given state, what it will be in the next instant of time. Is that clear? All right, so this is one way of describing the laws of physics. Write down all the states. Keep in mind what they stand for, of course. Remember that in this case, one stands for heads, one stands for tails, or whatever it happens to stand for. If it's the male, female, this could be an interesting case of, this would be a very interesting law of motion in that case. I don't think I want to explore that any further. If this were my undergraduate class, I would never have brought that up. This is the more likely law of updating for sexuality, female, male. So you see, simple laws sometimes apply, sometimes they're a little more complicated. Can you think of an interesting system that flip-flops like this? Offhand, I can't think of anything. I mean, it's obvious that it applies to a lot of things, but offhand, I can't. No, right. But yes. But if you're not intervening. I don't want you to intervene. This is the system by itself. If you had some peculiar light switch by itself, went back and forth and back and forth and back and forth in a regular way, but that's with day and night. You know, this is which? Well, there's a lot of states to the pendulum in between, but yes, you've got the idea. It's hard to think of a simple example, but I bet if we all go home and we came back next week, every one of us would have an example of we could call this the flip-flop. This is the flip-flop motion. This is the unmotion. Okay. Well, we can extend this. If we know what the space of configurations is and we lay them all out, either abstractly in our mind or actually just write them on the blackboard, then the motion of the system can be represented by a series of arrows, where I'm getting tired, but and so forth and so on.
You only need 2 to the 100.
Yeah. I don't know. Let's think of some possible motions of a 2-bit system. A 2-bit system simply has 4 states. Right? That's all we have to know. It has 4 states. Well, here's one possible motion. If we start with this configuration, we move to that configuration. If we start with this configuration, we move to that configuration, and so forth. If we watched what actually happened with time, the system would move from one configuration to the next around a closed loop. Now, the closed loop is not necessarily a closed loop in space. It's a closed loop in the logical space of possibilities here, logical space of configurations. That's one possible thing. Here's another one. Perfectly good. What this is it's a pair of systems, it's a pair of systems which are separately undergoing flip-flops. Each one undergoing flip-flops. This one is flipping and flopping. This one is simultaneously flipping and flopping. If we start over here, let's see what that stands for. That stands, for example, for both heads. It could stand for both heads. Then we go to both tails. Then we go to both heads, then we go to both tails. Or we could start with one head, one tail, and do this. That's what this is. This is a pair of systems flipping and flopping. There are other possibilities. So there are different laws of motion that the system, whatever it happens to be, could have. So when you specify a system, you not only have to specify what the states of the system are, but you'll have to specify how it moves. And how it moves is a rule for jumping from one configuration to the next. Now let me give you an example of a logically perfectly sensible rule, but which is defective from the physics point of view. Never happens in physics. We can do it, I think, well, let's do it with four states. With 4 states. Let's see how this went. Yeah, here it is. If you start here, you go here. If you go here, start here, you go here. Excuse me one moment. For some odd reason in my notes I've drawn, instead of a diamond shape, I've drawn a square. Let me go back. There's my 4 states. Okay? If you start here, you go here. If you start here, you go here. If you're over here, you go over here. And if you're over here, you go over here. All right, so now we can say what happens wherever you start. If you start over here, you jump to 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 here, you go 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 here. Notice you never come back to here. Okay? With this particular law. There's something different about this law than there is about the other examples. In all the other examples, well, can anybody spot what's wrong with this? Well, not what's wrong with it, but what's different about it. Well, it doesn't consist of loops. This is true. You can't figure out necessarily where you came from. You may be able to tell where you go next, but you can't always tell where you came from. For example, if you find yourself over here, you don't know if you came from here or whether you came from here. If you're over here, you have lost a piece of information. This is a motion which loses information. It loses information in the sense that you can't tell where you came from. There's no way to reconstruct the past, but you can reconstruct the future, or construct the future. Wherever you are, you're told where to go next. But wherever you are, you don't know how to get back. If you're over here, well, you know you came from here, but then you don't know whether to go back here or to go back here. So this is what is called an irreversible history. It's a history or a law which loses information. And at the fundamental level of physics, the fundamental level where you're really keeping track of everything, not where you're coarse graining or not looking carefully, but where you're carefully looking at every degree of freedom of a system, classical physics never allows the loss of information like this. There is a unique future point wherever you are, and there is a unique past point wherever you are. Okay? That is one of the laws. It's not necessarily a law of logic. It is something which is true of all physical systems, that they are reversible in that sense. Yeah. Let's say I change state twice. All right, and I'm over here. 1, 2, or 1, 2. I don't know if I came from here or here. Right. We could give this property a name. We give it the uniqueness of the future point and the uniqueness of the past point. We could invent a name for it. We could call it unitarity. Do you know what the quantum version of unitarity is? It has a name. It's called unitarity. Unitarity is a name I just made up. Unitarity is the quantum equivalent, which tells you that you can always reconstruct the past from the future. The state of a quantum system, you can either run forward uniquely or run backward uniquely. and you'll come to some unique previous state or future state, and that's called unitarity in quantum mechanics. But we haven't done quantum mechanics. Nothing's quantum mechanical yet. It's a kind of time reversal symmetry, or it's actually not a time reversal. Okay, so it's not a time reversal symmetry exactly. It's a time reversibility, I would say. This diagram has a sense of orientation to it. If I start something over here, it goes around this way. It definitely does not go around this way unless I reverse it, unless I look at it backward in time. So it's not precisely what you would call time reversal symmetry. Time reversal symmetry means that you could either go, in going into the future, you could go either way, but in this case, you only go one way. But it's the reversibility of the laws that, that you can find a reverse law. Given a law, you can find a reverse law which will take you in the backward direction. I think that's right, yes. Yes. Well, 2 arrows coming away from a point says, I don't know which way to go. Oh boy, do I go that way or do I go that way? So it's clear that that's not a law of motion. Okay?
No branching ratios.
No branching ratios. Oh, well, at the moment we're doing quantum mechanics, so I mean classical mechanics. It gets more complicated with branching ratios and. Let's see, classical mechanics is less fundamental than quantum mechanics. All real systems are quantum mechanical. The question why some of them suppress the quantum mechanics and you don't see it is a question which we'll try to answer as we go along. But we might ask it at the quantum level, and at the quantum level I think we can give a better answer. But ultimately, at the end of the day, it seems to be a law that basically says that forward in time and backward in time are I won't say equivalent to each other, but that there's no really preferred sense in which forward in time is different than backward in time, even though it feels like there is. This is the question that took 20 years to answer, and the answer is, in my opinion, no, it is not possible, but it was one of the great questions of physics that took a long time to answer, and I'm not going to get into it now, but it might be an interesting thing for us to explore toward the end, after we've talked about quantum mechanics. We have to talk about quantum mechanics before that makes sense, that question. Yeah. I think they're all Newtonian in a sense. Newtonian to me simply means that there's a definite state for a system, that it evolves with time according to a definite law of deterministic. That's the right word, yeah. But I think you can think of more complicated situations. You just can start drawing some diagrams yourself and see what makes sense, what's reversible, what's not reversible. But yes, you're right, that is true. It loses the information as to where you came from. The system.
That doesn't after the first step.
Yep.
That's not a part of the system anymore.
What do you mean it's not a part of the system? The system started here, it went to here, it went to here, it went to here, it went to here.
Anymore. So if you come and observe it at some later point in time, you won't find that point.
You won't find that point ever again, right? Right. But the main point is you've lost the distinction between the two possible starting points, whereas in all the other situations, if you know where you are and you know how many steps you made, you can say where you were. Well, I think for a long, long time, Mr. Stephen Hawking thought that this is the way black holes work. So not so clear, not so clear. Okay, yeah, good. So let's talk about that. If I take a bunch of molecules in a bathtub, I don't know, what's a good example? Well, let's take the molecules in this room, and I start them all out in a certain configuration, very definite configuration. I put them all up in the left-hand corner of the room there, and I let them go. after a while the room will be full of air just like it is. If I put them up in that corner of the room over there and let them go, after a while, same thing. Put it up in that corner. After a while, same thing. So it looks like we've lost information. But in fact, that's not true. If we followed every single molecule and we followed it in infinite detail, with infinite precision, which we don't do, of course, then we could reconstruct, by running everything backward, we can reconstruct the fact that the molecules may have come from that corner of the room. It's prohibitively impossible to do in practice, but in principle, following every single detail of every molecule. Now, what really happens in the real world is we lose information because we lose the ability to follow the details. Not because the information gets lost, but because we lose the ability to follow the information. That's where the second law comes, when you start losing the ability to distinguish different states. So we don't distinguish whether, in our coarse-grained picture, we don't distinguish the different detail at the level of the molecular detail. And so it looks like different configurations become the same configuration, but that's only because we simply don't look carefully enough. It's because we're lazy. Do you need an infinite number of bits to... You mean in a real room like this? No, because of quantum mechanics. Because of quantum mechanics, no. But if it were not for quantum mechanics, yes, you would need an infinite number of bits. Now, what does that mean? That means that you have to specify a bunch of real numbers precisely, with tremendous precision. You have to precisely prescribe the locations and also the velocities, but in particular the locations of every single molecule with a tremendous amount of precision. And the longer that you want to track the system, the more precision that you need. So ultimately, to track a system for a long time, you need to specify with infinite precision the exact positions of every point, of every molecule. That means you have to give a set of real numbers. A set of real numbers involves, as you say, an infinite number of bits. So the answer is for a collection of real particles moving around that you really try to follow classically, depending on how long you wanted to follow it, you would need more and more bits to describe it. Yes, that's right. If the room were really sealed, let's idealize this room so that nothing can get into or out of the room. All particles bounce off, reflect off the walls of the room, so that it's an entirely sealed up room. Then the room can be described discretely because of quantum mechanics, at least up to some energy. If we know that the energy isn't arbitrarily high, then we can describe it by a discrete collection of variables that has no exit. So let's see. So we could, to make such a thing, we could just reverse all the arrows. Here is an example.
It doesn't actually have no exit, it just exits back to itself.
No, this one has no exit.
No, it just exits to itself.
Well, then if I want it to exit to itself, I have to do this.
Yeah, that's what I'm just saying.
We could do that, but as I drew it, it had no exit. Huh? But let's think about what it means. I'm not too interested in what here. The question is, what happens when you're over here? All right? When you're over here, you have two ways that you could go, and you don't know which way to go. So it's not deterministic. It doesn't know whether to go this way or this way. It might go half the times this way, half the times this way. You might need some statistical rule. 50% of the time or 30% of the time it goes this way, 70% of the time with random statistics. That would be non-deterministic. Okay? So it seems that the real laws of nature are both deterministic forward in time and backward in time. That's the implication of not having loose ends floating around like this. That they're deterministic either way, so that wherever you are, you can either trace forward uniquely or backward uniquely. And that is all of classical physics in a nutshell. You've now taken a complete course in classical physics. There's nothing that does not fit that pattern, at least to an arbitrarily high degree of approximation. Let's take a 7-minute break. Well, I was going to jump to quantum mechanics, but before I do, I want to do a little bit of mathematics, elementary mathematics. Most of you know it, but nevertheless, let's lay it out. Matrices and vectors. At the moment, I'm not going to mathematically define a vector in any sort of sensible, even approximately rigorous way or abstract way. I'm just going to tell you. A vector is a sequence of numbers, a finite sequence of numbers. And you can represent it in a variety of ways, but I'll give you two ways to represent a sequence of numbers. The first way is to write them one after another. Let's just give them names. I don't want to call and by numbers now. At the moment, I mean real numbers, as opposed to complex numbers. I don't mean zeros and ones. I mean arbitrary sets of real numbers. They could be zeros and ones. But zeros and ones are fine, but just general numbers. So I just lay them out. What should we call them? Yeah, they're called components, but I want a letter for them. A is good. So A1, A2, A3, A4, and just put something around them to surround them so that we know. This would be a 4-dimensional vector. All right? Why 4-dimensional? Because it has 4 components. Don't try to visualize vectors now. There's no value at all for our present purposes in trying to visualize these as pointing in space or anything like that. They're just lists of numbers. Okay? Lists of, that's one way. Okay? There's another way that we can list the same set of numbers. Put them in a column. A1, A2, A3, A4. Same information in them. I mean, and I'm not talking about information in the abstract sense that I used before. Same thing. Sometimes it's useful to write it this way, sometimes it's useful to write it that way. You'll find out as we move along. When it's written in this form, it's called a row vector. When it's written in this form, it's called a column vector. What we're actually talking about now is notations, neat notations for doing certain arithmetical operations involving collections of numbers.
But isn't one of those the dagger of the other?
When we get to complex numbers, we will then use complex conjugate notation, yes. But for the moment, let them just be real numbers. Okay? Now, there's another concept now called a matrix. And think of a matrix as the following way. A matrix is a thing which acts on a vector to give another vector. All right? So it's a kind of machine. You put the vector into the machine and out pops another vector according to a particular rule. Oh, no, sorry, before we do that, let's imagine a particular column vector and another different row vector. Different row vector has different entries. Not the same set of numerical entries, but a different set of numerical entries. So let's call them B. B1, B2, B3, B4. These could be 6.01, 5.97, 3.04, and A1 could be 7.8, A2. None of them, they could be the same or they might not be the same, the A's and the B's. This is some particular row vector and some particular column vector. there's a notion of multiplying a row vector by a column vector. And the notion of multiplying a row vector by a column vector is as simple as the following simple operation. You take the first entry, incidentally, the dimensionality of the row vector and the dimensionality of the column vector should be the same. That means that they should have the same number of entries. Not necessarily 4. It could be 5, 6, 7, in which case they would be 5-dimensional vector spaces, 6-dimensional vector spaces. This extends to any number of entries into the columns and rows, but the rows and the columns should have the same number of entries. All right. There's the notion of the product of a row vector and a column vector. It's called the inner product, and it's very simply constructed. You take the first entry of the row and multiply it by the first entry of the column. You add to that the second entry times the second entry, plus the third entry times the third entry, plus the fourth entry times the fourth entry. So the product of these two, which you could just write as B next to A, that product, the inner product, is B1A1 plus B2A2 plus B3A3 plus B4A4. It's a number. It's not itself the product of these two vectors. The inner product is not another vector. It's not a matrix. It is just a number. The numerical value is just gotten by adding up the column, the row times the column in just this form. B1A1 plus B2A2 plus B3A3 plus B4A4. Is that clear? Don't ask me why. That's definition.
Is this what you call the dot product?
Yeah. Yeah. If we were talking about ordinary vectors in space, it would be the dot product. Yeah. Yeah. More abstractly, for abstract vector spaces, it's called the inner product. But yes, it is the same as the dot product for three-dimensional ordinary vectors in space, where these would be the components of the vector. Yeah. Okay, now there's the concept of a matrix. And a matrix, as I said, is it's an operation that you can do on a vector to give a new vector. All right? But it's not any old operation. There are a particular family of operations that are characterized by matrices. A matrix is represented by a square array of numbers. Let's call the entries M. All right, so in the first place we put M11 to indicate that it's in the first row in the first column. Then M12, then M13, then M14. Okay. What should I call this one? 2-1. It's in the second row, but the first column. This is in the second row, second column. Second row, third column. Next one, M31, M32, M33, M34, and M41, M42, M43, M44. Now, as I said, I've chosen 4 dimensions just arbitrarily. 4 is about as big as I want to handle on the backboard, and it's big enough to be a little abstract so that it's general enough to see what's going on. All right, that's what a matrix is. That's all it is. Now you can think of each column as a column vector whose components are labeled by the first entry here. Okay? Each one of these can be thought of as a column vector where the first entry labels the column entry. Or you can think of it as a collection of row vectors where it's the second entry which labels the component. Either way, You can think of it both ways at the same time, a collection of column vectors or a collection of row vectors. But altogether, it forms a matrix. Now, matrices can multiply vectors, so let's put a vector over here. A1, A2, I should line them up more carefully. A1, A2, A3, A4. And when you, I don't know, I've done a reasonable job of keeping rows and columns underneath and next to each other. But if you like, draw some imaginary lines to separate them into rows and columns. All right, this matrix acts on this vector to give a new vector. What is the new vector? And here's the rule. I've made the vector wide because each entry is going to be a fairly complicated expression, but it is just another vector. It's another column. It's a column which I've had to draw wide in order to be able to fit in everything I want to write down. Here's what you do. If you want to find the first entry into this column, into this row, you take the first row and you multiply it by the column. The inner product of the first row with the column here. So what is that? That's M11 times A1 plus M12 times A2 plus M13 times A3 plus M14 times A4. In other words, you take all of this and you multiply it by this according to the inner product rule, and that gives you the first row. M11 A1 plus M12 A2 plus M13 A3 plus M14 A4. Now you want the second entry into this new vector over here, done exactly the same way, except you go to the second row, and you take the second row and multiply it by the column. That's going to give you, I'm only going to do two of these, the rest you can do yourself. M21, again times A1, plus M22 times A2, plus M23, A3, plus M24 times A4. And the other two entries you can figure out. You get them by multiplying the next row by the column, and finally the third row by the column. That gives you a new vector. It's a way of processing a vector to produce a new vector. I will give you some examples as we go along. It's a rule of multiplication which is very useful. The reason it's defined is because it's useful, and we're going to see how it's useful by using it. Let me give you an example of how a matrix, how the idea of a matrix can represent the time evolution of the configuration of a system. Supposing, again, we have our configuration space. Let's label them. Let's label them. The first configuration, the second configuration, the third configuration, the fourth and the fifth configuration. These are not points of space. These are configurations of a system which has 5 distinct states. And let's take a very, very simple law of evolution. The first one, if you start here, you go to here. If you start here, you go to here. If you start here, you go to here. If you start here, you go here. And what do I do from here?
Go to Excel.
Go back. No, well, no, that one, that's no good. That's disallowed, I think. Is that disallowed? I think that's disallowed. I think that's disallowed. Yeah, that's disallowed because if you find that's not reversible. That's not reversible. That's not what I wanted to hear. What I wanted to hear is that you go back to here. Okay. So this is just a 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes back to 1. It's a cycle. Okay. Here's another way to represent the same thing. We can represent the state of the system by a column vector. And the column vector, we simply insert a 1 someplace. If I want to represent the first state over here, I put a 1, and then a bunch of zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This simply represents the first state. What about the second state? The second state I'll represent by 0, 1, 0, 0, 0. The third state by 0, 1, and so forth. So the states of a system can be represented by a column, but a particular kind of column, a column with all zeros and a 1 someplace. Where is the 1? Namely, whichever state you're focusing on. If you're focusing on the 5th state, put the 1 in the 5th entry here. Okay? Now, what is this rule of evolution? The rule of evolution says that if you have a 1 someplace, then in the next instant of time, the 1 moves down. So if you start here, the 1 moves down to here. In the next instant, it moves down to here. Next instant, it moves down to here. Next instant, it moves down to here. Then where does it go? Up to the top. All right. So there's a procedure that you do on this column to tell you where the system goes in the next instant of time. That process can be represented by a matrix. So let me show you the matrix that represents that. The matrix is an operation on a vector which you can think of in this case as the updating operation, the operation which updates the vector. So here it is. Let's see, we put 0, 1, 0, 0. This is 5-dimensional, so I need 5. 0, 0, 1, 0, 0. 0, 0, 0, 1, 0, 0, 0. I'm sorry, I'm going to make this 4-dimensional. I'm getting sick of it. I don't like 5 dimensions. 5 is too many for me. Right. 1, 0, 0, 0. Let's try it out. Let's try it out on this vector right over here. This represents the third state. What happens if we act with this matrix on the third state? Let's just try it out. Let's see what we get. Well, the first entry up on the top is gotten by taking the top vector and multiplying by the column. 0 times 0 plus 1 times 0 plus 0 times 1 plus 0 times 0. What's the answer? 0. Next place, 0 times 0, 0 times 0, 1 time, 1 time, whoops, whoops, whoops. I did it, okay. Yeah, right. Instead of going down, it's going to go up, but it's okay. Up and down, we just turn the whole thing over. Would you prefer? Let's just let's get it right. Let's get it right. 0, 0, 0, 0. Where did I have it before? I had it over here. Yeah. 1, 1, 1, 1, and then up here. 1. Okay. So let's start over again. What's up on the top? 0 times 0, 0 times 0, 0 times 1, 1 times 0. We're still okay, 0. Next one, 1 times 0, 0 times 0, 0 times 1, 0 times 0, still 0. What about the third place? Oh, please, 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 God. 0 times 0, 1 times 0, 0 times 1, 0 times 0. It's still 0. But now in the last place, I have 0 times 0, 0 times 0, 1 times 1, and 0 times 0. So 1. The column has moved down 1 step. Now you can check for yourself. Here's your homework. Check that any place that you put this 1, it will move down by 1 step till it gets to the bottom. And then it'll recycle and go up to the top. Okay? So that's a little thing to check. In fact, you can put in any numbers here. Only zeros and ones may make sense, but we could put in any number, A, B, C, D. And what will come out over here is everybody will move down a step, A, B, C, but then D will move up to the top. So if you put a 1 in any one of the places, it will slide down 1 unit and then reappear at the top. The point is that the evolution of systems can be represented by matrices. Matrices of a particular kind. In classical physics, in this kind of classical physics, there are always just 1s here. Quantum mechanics is more complicated and more difficult, but in classical physics, sprinklings of 0s and 1s so as to make each state shift into the next one. Okay? That's an example of the use of matrices in classical physics. So far, no quantum mechanics, just pure classical physics. There is an interesting, well, all right, this will do for the time being. We'll come back to it. So that's an example of matrix algebra, matrices multiplying vectors. What about matrices multiplying matrices? Why might we want to multiply matrices by matrices? Well, here's the idea. Supposing we wanted to upgrade or update a second time. To update a second time, what we would do would be to apply the same matrix to the resultant that we got. In other words, let's write it this way. Let's write it abstractly. We have a matrix M, which we multiply by a vector V to get a new vector V prime. Okay? That's just abstract notation for writing a matrix and a vector and getting a new vector. That's updating the vector V to a new vector. Let's update it again. Let's go one more interval of time. How do we do that? Well, what we do is we write M times V prime equals V double prime. We would do the same updating trick, except now update V prime instead of V, and we would get V double prime. V double prime being the state of the system after 2 units of time. But we could also write that by realizing that V prime is M times V. We could write this as M times V is equal to V double prime. This just means we apply the matrix twice. We can also think of it as squaring the matrix M and then multiplying it by V. So how do you square a matrix? Or how do you multiply one matrix by another matrix? This is what you would do if you would want to update twice, once with one matrix and then once with another matrix, or the same matrix. How do you multiply matrices? And the answer is basically the same kind of rule. I will do it now for 2 by 2 matrices because it's getting too complicated even for 4 by 4 matrices. For a 2 by 2 matrix, we have M11, M12, M21, M22, let's call it some other matrix n, n11, n12, n21, n22. The result of multiplying a matrix by a matrix is another matrix. All right, it's another matrix, and we do it in a very similar manner. Supposing we want the 1, 1 entry here. We get the 1, 1 entry by taking the first row and multiplying it by the first column. M11 times N11 plus M12 times N21. Same kind of inner product, and we put it over here. Now supposing we want the next entry. For the next entry, we take the first row, because after all, we're interested in the first row up here. We take the first row, but multiply it by the second column over here. So what would be over here would be M11 times N12 plus M12 times N22. I'm not going to write it all out. Now we can move down to the bottom. To the bottom, if we wanted this entry, we would take the bottom row and multiply it by the first column. If we want the last entry over here, we would take the bottom row and multiply it by the last column. So we multiply matrices by the same kind of pattern that we multiplied matrices times vectors. We can simply think of it as multiplying this matrix by this vector, putting it over here. Multiply this matrix by this vector, put it over here. Okay? So there's a notion of multiplying matrices. And what multiplying matrices does is it gives you a new matrix which updates you not by one interval of time, but updates you by 2 intervals of time. If you wanted to short circuit the problem of updating, and you wanted to update the state of a system 5 units of time, what you would do is multiply the matrix together 5 times. That's, you do it in sequence. First, the first times the next, and the result times the next one, times the result times the next one, and you can work out what the matrix is, which would take you from the state of a system at an instant of time to a state of the system 5 instants later. So matrix multiplication, multiplying matrices by matrices, is also an important concept. Okay. One last example of matrix algebra involves row vectors. Supposing you have a row vector and you want to multiply it by a matrix. The rule is you write the row matrix first, B1, B2, B3, B4, and then you write the matrix, M11, M12, M13, and so forth. M14, dot, 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 dot. Tired of writing M's. Well, what's the result going to be? The result is going to be a row vector. And here's the way you get the entries of the row vector. The first entry of the row vector you get by taking the original row vector and multiplying it by the first column vector over here. That product is the first entry. Then you take the original row and multiply it by the second column. That gives you the second entry. Then you take the original row and you multiply it by the third column. That gives you the third entry over here, and so forth. You see the pattern? It's always multiplying rows by columns and putting the result in the right place, in the right row and column. In this case, a row vector times a matrix is another row vector. A matrix times a column vector is another, here it is, a matrix times a column vector is another column vector. And a matrix times a matrix is another matrix. Get familiar with that. Work out some examples. Work out some examples of your own devising. Just put some numbers in. Multiply row vectors times matrices, matrices times column vectors, and matrices times matrices, and get the experience of working out how these things work. Do it for 2 by 2, for 3 by 3 matrices, and you'll get familiar with it because we will use it over and over and over again. In fact, that's the primary mathematical operation of quantum mechanics, is multiplying rows and columns times matrices. If you know how to do that, and you're familiar with it, and you can read off the answers easily, you've got all of the basic mathematics of quantum mechanics. It would help to have a little bit of calculus to go with it, but the basic new thing is matrix multiplication and column vectors and row vectors. So please, practice with it a little bit. I should have made up some examples for you to do, but you can make up your own. They're very straightforward. Okay, we're getting close to 9 o'clock. Are there any questions? Next time we're going to start talking about qubits, quantum bits, and how quantum bits are very different than classical bits. Question? Yes?
What's your name?
My name? Leonard Susskind. Or Susskind. You, if you like, polishing the apple for the professor, you can call me Leonardo. I like that very much. Well, you mean, say it the other way. What restriction does reversibility place on him?
Oh, yeah.
Yeah, yeah. That it have an inverse.
Okay.
Right. Yeah. But I mean, in a more, if I were, in a more abstract sense, the answer is that it should have an inverse, that the matrix should have an inverse. The inverse, of course, is the thing that takes you back. Not all matrices have inverses. So, and you know what an inverse is? Yeah, okay, good. And we'll, if you don't, we'll come to it. Any other question? Yes, that is a good question, yeah. The final exam is buying me lunch. Right. That's a lot of lunches out there, boy. Look, nobody asks me about grading the class. Nobody, I mean, a lot of you have been here before, so you know my policies. My policies are you're here to learn physics. There is nobody here who is here for a degree, or if you are, then I'll be glad to give you a numerical grade if you need one. In fact, if everybody needs a numerical grade. I know that there's an enormous difference in the level of preparation of different people here. And to compare you in an exam setting wouldn't make sense, because I do know that there's an enormous difference. I know that everybody here is here because you want to be here and you want to learn physics, and not because you have to be here. So my policy is to either not grade the course at all, or if somebody needs a grade in order for some particular purpose, to give a D minus, lowest possible grade, lowest possible passing grade. All right, so it's. I didn't tell you what it's for yet. I gave you, that's right, I gave you an example of how you can use it to implement the idea of updating a vector from one instant to another. It's one example, but I haven't told you yet why we're doing this. I often spend an hour talking about qualitative aspects of physics. In this case, it was, how do you abstractly think about deterministic physics? abstractly in terms of bits and so forth, and then spend some time doing some mathematics, which really I won't tell you what it's for until the next time. But I want to make sure, since I'm going to start doing some quantum mechanics the next time, I want to make sure that everybody will recognize the little algebraic little bit of manipulations that we'll do and have the mathematics for the next time. So it's really for the next time that I set this up. Yeah.
Do you promise to tell us next time why?
I think you will see. I think it will be clear. I think it will be clear. Right. I think it will be clear. Yes, I do promise to tell you why. Yeah. No.